Welcome to ELE 201, Information Signals. As the class began, we were listening to some music. The Hotel California, one of my favorites. Sound recording technology has gone a long way since the phonograph first recorded sound. What we'll do first is open up the sound file for Hotel California in some music editing software. That way we can see exactly what signal, what data we're working with. So now I'm going to pull open some open source software, Audacity. Now, sound is just fluctuating pressure waves in the air. What we see here is the sound that's been captured by the microphone as a graph over time of these fluctuating pressure waves. We can listen to it.
Watch the sound. Okay. You heard it before, so.
So as you see, this is really just a graph of the fluctuating waves in the air. Now, several of you have probably played with this before. For those who haven't, let me show you. You can zoom in so you can see the finer details of the sound. At this view, it's not very informative. But if we zoom in, then we can see the beat and the intricate details. We can keep zooming
like that. Sometimes zoom back out. I'm going to need one of you who's this before.
Now, if we zoom in far enough, we'll see that, in fact, this is a sequence of individual numbers, these dots here that we see. Because this is a digital recording, it's actually a sequence of numbers, and the graph just tries to interpolate between to show us what the sound actually would have been between the samples. Now we can actually redraw. We can actually change these values if we wanted to be weird. So here's a little tool that lets us rewrite the values of the individual samples. One thing I didn't mention was that there are two streams of data here. There's the one on top and one on bottom. And that's because this is actually a stereo recording. There were two microphones used. This gives it stereo spatial features to the music. Notice that the two signals are similar, especially when we're zoomed out, you'd see they're similar, but they're not exactly the same. During playback, these are played to different speakers, your left and right speakers. So here, I have to zoom in to be able to actually rewrite it. Okay, there. Making my own modifications to the sound. Now, this is a very short window of time. So when I zoom out, there, you see what I've edited. It's all condensed in one little moment of time. So, of course, this short period of time, it's not going to be easy to hear. When I play it back, it's just going to sound like a little click or clap. It's not playing through the speakers as I want it to. Well, for whatever reason, this is not playing out through the room speakers. Oh, I see. There's a button underneath play here that should let me pick the output.
It's going to be really loud now, maybe. What? I can hear it here. Okay. Does anyone hear a little tap?
I hear that little tick.
So that's the nice sound.
That's the editing I did. So this was an example of signal processing, which is really a big part of what this class is about. Of course, what I did here was manually process the signal, and that's not an effective way to do it. What we really would like is an automated process that looks through the signal, finds the right moments in time to make changes, uses some mathematical tools to make the manipulations that we want, and also understanding what they're going to do. We also would like to analyze signals using mathematical tools, not just to manipulate them, but also just to dissect them, understand them, pattern match them. So let's talk about some examples of signals. A signal, the definition of a signal is very broad. It could really be any function or sequence of numbers. The independent axis might be time, it often is. And if it's a sequence of numbers, then think of the indices as time indices. So here's an example of just an arbitrary, an artificial signal that I created. Now, one very common thing you might want to do is smooth a signal. And you see here I have a red line going through the middle that kind of represents the smoothed version of this blue signal. So one motivation for this is maybe you're trying to measure something you expect to be smooth, but your sensor measurements jump all over the place, and you want to interpret that as noise. So aside from drawing this by hand, can you think of an automated way of smoothing? Yes, averaging. Yes, that's a great example. And how would you do averaging? Okay, so you mean not to average the whole signal, but average locally around the point that you're trying to smooth. Perfect. So this technique is going to be directly applicable to what we're talking about in this class. Now, you actually can get different effects depending on how you do the averaging. For example, you could just, for each output point, you could just go a certain number of samples or a certain length of time before that point and after that point and just take an average of your signal. And that average then would be your output at that point in time, or that time index. That's one way to do it. But you could also do a weighted average. You could count the points closer in time more heavily and the points further away in time less heavily. So in general, this sort of weighted averaging is something known as convolution, and we're going to study that in detail. And the great thing is that convolution can be understood very well through the math tools we're going to cover in this class, in particular the Fourier transform. So you'll know exactly why or what the effect will be of using one sort of weighted average versus another. Can you think of another smoothing technique that's not average, or at least not the normal mean? Okay, that is to use the median. So the local median is a way of doing smoothing that sort of removes outliers. So if you have something that's far away from your true signal, but it infrequently occurs, then it'll be removed completely from the median filter. It's a very useful filter. However, it is out of the scope of what we'll learn in this class, so there are limits to what we learn in this class. It's very, very broad, but limited. Now, this picture depicts what we would call a system, which is usually studied along with signals. if we're building a system that takes inputs from, let's say, sensors from the world and it acts on the world through actuators, and in between it does some processing, then really this is a large part of what engineering is about, is building systems like this. So we might want to know, how do we build a system to do what we want it to in terms of signal processing? Or we might also want to know, if you have a system, maybe we didn't build it, maybe it's just a room and you want to understand the echoes through a room or all sorts of physical systems, then again, you would want to be able to understand what is it going to do to a signal. So that's why systems and signals are studied together. So here's an example of a signal being image. And it's a processing that you might want to do of deblurring an image. So blurring happens when a camera is moving while an image is taken. So here's a couple examples of blurry images. And next to them are images that have been deblurred. You'd like to just do a process, a mathematical process that can recover a sharper image from a blurred image. There are tools to do this. Adobe Photoshop has tools, and they come out with new ones each year and improvements. So it's still an active area of development. And we will see some simple techniques that can at least get started in deblurring an image using just the basic mathematical tools that we learn in this class. Here we see a touch surface. And of course, this is the job of sensors to figure out where fingers are touching the surface, figure out whether there's multiple fingers, whether gestures are being made. And all of that has to go beyond just the sensors, but also the processing of the information signal coming from the sensors to detect what the intention is of the movements and to distinguish touch from just some noise in the sensors and so forth. So if you think about it, a large part of any engineering device, including a touch surface phone, for example, involves signal processing. Here next we're looking at radar and tracking. Of course, the idea of radar is that a signal is actually sent out from the radar device, some electromagnetic signal, radio waves, microwaves. They hit an object and they bounce back. And depending on the timing, depending on the Doppler frequency shift, you can infer things like direction, distance, speed of the objects that were hit. So this is a direct application of signal processing. Beyond just inferring those things that I mentioned, you also might want to track an object over time. So you'd say, well, if your radar signal said it was at a certain position and velocity at one moment in time, and another moment of time if it's in an inconsistent position and velocity, then you would use some sort of smoothing technique, which is another signal processing application to track and remove whatever noise is possible out of your radar. So the material we're learning in this class is directly applies to this type of technology. Absolutely. Now, there's a part of what we won't cover. Signals and systems in general uses a lot of probability. And we're not assuming that you've studied probability, so we're going to be learning things that do not, for the most part, do not utilize probability, which means you wouldn't be able to derive all of the best state-of-the-art techniques for tracking and radar without going into probability. Okay, beyond that, digital communication is another big application area of signals and systems. So communication technology is designed in a way to carry information that's robust to errors due to noise, interference, multipath. So here we've depicted some wireless cellular communication, some Wi-Fi, some wired networks, and all of these use signal processing and signal analysis in many ways. For wireless, you're directly designing signals to be carried by electromagnetic waves in such a way, like I said, that will be robust to noise. And one part of that is that a wireless signal can bounce off many paths to get to its destination. And this appears as a bunch of echoes in the received signal. And echo cancellation is something that's very well handled and understood through the Fourier transform, which is, I guess this is the first time I've mentioned that so far, but that's the big emphasis of this class and what you're going to become very familiar with. Another aspect of communication is sending multiple signals over the same resource. For example, the same airwaves. You can use different frequencies and channels to send multiple audio signals, for example, at the same time. And that's what happens when you do FM and AM modulation over the radio, for example, or cellular phone modulation, where many of you can use your phones at the same time from the same room. It doesn't interfere with each other because we design the signals that way. And this will be something you understand very well from the material of this course.
Multipath in cellular, okay, in wireless. And what you can do is actually use, this is the first time of many times I'm going to use the word Fourier transform. That's actually a major emphasis of this class. And you can use the Fourier transform in filtering to address things like multipath, echo cancellation, things like that. MRI is a very very nice. If you know much about it, how many people have had an MRI? Okay, something like 5, 7, 8. Okay. So MRI, of course, can give either a 2D slice or three-dimensional capture, which it'll display as two-dimensional slices anyway. And the way it works, gets the information out of what it's trying to image is it actually images the molecules that are inside the object. Usually it's water. And the magnetic moment of water allows you to get a signal out. Okay, so what you actually do is very different than something like radar and how much they absorb a wave. So X-ray is just you send X-ray light through, and it gets absorbed more by bone than other things, and you get the contrast that way. You put a film on the other side. Pretty straightforward. Ultrasound is like radar. You send these sound waves, and they bounce back based on the density of the material. You know how long it took to do something like radar. But MRI is very different. You actually send a non-invasive energy wave in. You do some radio frequency wave, but it's not meant to bounce back and give you an image or anything. All it does is allow the body to resonate because they're in a very strong magnet. And if you put a magnetic moment in a magnet and you knock it out of alignment, if you want to align with the strong magnet it's in, if you knock it out, in order to align back with the strong magnet, it rotates on its way down. Okay, and that rotating, you can think of it. Basically, all the water sinks back to you. You can pick that up with your antenna, and you can then come up with an image. The cool thing is that this technology so directly uses the Fourier transform. In fact, that's almost all it requires once you send your signals out. And we'll talk about that a little bit, just to give a little application of the Fourier transform later. We'll just talk about why is the Fourier transform used here. Okay. Image recognition, face recognition, these are examples of signal along here. Another signal, consider stock prices over time as an information signal. Really, anything can be considered an information signal. And another good example is flow of internet traffic over the internet, okay, as measured over time. Now, often these information signals time sequence. Often the independent axis is time, and in fact, even when it's not, you just kind of say time because it's easier to say. All right. So the images time is not your axis, right? If we go back to processing, well, let's say this image. So we think of this as well, it is a sequence of numbers, or even if you want to snapshot by film or something. Then it's a function where the domain is two-dimensional, right? And the range of the more than one dimension, but if it was the black and white image, then it would be very easy to think of the range with the whiteness of the image at each point. Right? The domain is two dimensions. And it's not time. It's space. Okay, so you can have anything you want as the however, I will always just say time because I forget to. So even in this case, for example, I mentioned signals, and again, technically this is a discrete time signal because, well, for one thing, if I zoomed in, I would see that there's a value of one pixel, a value of the neighboring pixel. There's nothing in between, right? And that's why we call it discrete time. However, this is a perfect example where I'm saying time when really time is not what we're talking about. It's discrete space, but also discrete time. A quick example of how this signal processing could be applied beyond just pretty or whatever. This actually applies to control settings as well. And towards the end of this class, we're going to have a couple of weeks where we try to stable. This picture is meant to kind of illustrate how signal processing becomes related to control. These are the shocks in a car, and the incoming signal is, let's say, the height of the road. This is a signal where the independent axis, I guess, is the car is driving at a certain speed, so you can convert it to what will the height of the road time that the tires hit it. That's the incoming signal. And you want the rider's comfort in the car to be, you want them to have good control, but also comfort. So maybe you don't want them to. And that's what the shocks are designed to do. They process this incoming signal so that the motion of the car, which is the outgoing signal you can think of, is somehow optimal for comfort. All right, and this is actually a great example because the motion of these elements is you can motion if you're talking springs and damping constant. Familiar with this physics, and so in fact, we will become very right. So knowing how the input will be affected by a system, that'll be something we can do in this class. And again, the Fourier transform. In fact, we're going to generalize the Fourier transform to a Laplace transform, and that'll help us with control. Also, it helps you understand circuits. So experience with capacitors and resistors and inductors. How many people do? Maybe you took a class last semester, or maybe not. And you know that these things, you can understand what happens when you put them together. They can resonate at various frequencies. They can do all sorts of things. If you have feedback, like this diagram shows that the output feeds back to the input, you can cause a system. Mathematics of this course, the Fourier transform, is going to give you another way of looking at circuits, where it'll give you a new understanding of where the formulas came from when you studied. And it's used to design systems like this, make them stable. So, okay, here's another control. Okay. I guess the sample is pretty small. I did grad school at Stanford. So if you don't know what this is, you stand on it, you lean, and it keeps you up. Keeps you up even though you're just standing on it. But when it's on, it moves to keep you balanced, and of course lets you lean and steer, and it'll mode of transportation. Um, so this is a very it's called the inverted pendulum. And the inverted pendulum problem is just what the picture shows. Usually you have an apparatus that's holding up a rod on a hinge of some sort, and there's no motor holding it up, so it would just fall loosely. So everyone is done, and you watch it and you try to keep it down. It's a fun game, but the idea is to design a circuit or a computer or not too hard, and we will hopefully do that as a demo in here at some point. We actually have a bunch of equipment that any of you could use if we set it up in the lab, or you can play around with the inverter, program it, try to get it to do things like balance and so forth. We used to use that. So I'm not sure, they might be discontinued, but it's fun. Here's another example where control, just to kind of show off what control can do. This is from UCSD, some robotics lab there.
Meet Switchblade, a unique agile robot from the Coordinated Robotics Lab at UC San Diego. The treads provide traction over a variety of terrain, but Switchblade has another trick up its sleeve. Each tread assembly can pivot relative to the central chassis. We can use this ability to change the center of mass and climb over obstacles. Using internal sensors, we can also balance on the end of the treads and stand upright.
Think of time we won't watch the whole thing. All right. So back to here. Okay, and we already mentioned sound. Sound will be actually a prime example. It's very easy to work with. We're going to manipulate it. We're going to be able to hear it, and so we're going to use this mostly in the labs that you do. We'll be using sound. We'll often just use it as an example. Okay. Even though it's one-dimensional, and of course there are very interesting applications of two-dimensional image. Even beyond the image, you go to video, and now you have a time dimension as well. We really, even if we just focus on one-dimensional signals, we're going to learn things that translate over to higher dimensions, and it'll get just as much use out of studying the one-dimensional signals. Okay. Not supposed to say. I'm going to cover the bottom. Okay. Okay. The upper graph here is just a signal I made up. Right. I just created some signal. Now this might be what it looks like if you record, say, yourself. If you zoom in enough, it might. You see that it's periodic. It repeats the same shape over and over. And so that gives it a certain frequency. How often does it repeat? If this were sound played through a speaker, that repeating frequency would be the pitch of the sound you're hearing. So higher notes repeat faster. But there's more than just pitch in this signal. There's the shape during that period. What's that shape going to affect? If pitch is just the frequency, then how do we hear anything else besides the pitch? What is that? Just say it again. Yeah. So the sound, the characteristic of what you're hearing. For example, instruments sound different. People's voices. And that's all captured in there. Now, when I was an undergrad, I really enjoyed playing with oscilloscopes, actually, because I would, hook up a microphone, make some sound. What does that look like? I want to know what's the difference between E and ah. Those are both the same pitch. What makes them distinguishable? And it's actually fun to play with, and you're going to do this in your lab, actually. Not with the oscilloscope, but you'll play with sounds in MATLAB. But there's a nice way to look at these signals, better than just looking at them as a time series. Turns out that this one that I created is nothing more than 3 sinusoids of varying amplitude and phase added together. Okay, so here are the 3 down below. That's the dissection of this signal up above. The sum of these things is exactly this. But now this is a much easier way to do this. What this is it's one. You see the blue here is the same frequency as the pitch. And you see that the red and green are higher frequencies. In fact, they are multiples. And so now, rather than thinking of this weird shape and trying to figure out what does that bump mean there, what does this mean here, it turns out that doing it that way is not going to help you understand what this sounds like. Because I can get 2 sounds that sound the same to you and look very different. Okay, so that's not the right way to go about it. But the magnitudes and phases, this interpretation actually does tell you a lot about how it's going to sound. This would be a way of analyzing the signal if you first dissect it into sinusoidal components. Okay, that gives you a way of identifying what the sound is like, where you could automatically say, "Oh yeah, this came from a saxophone," or "This is the sound, the vowel." Great. Now I need to get into some material because this class is short. I used to teach 80-minute lectures, so. Let's move along to, okay, let me tell you some things about the course logistics first, and then hopefully we'll have the complex numbers a little bit. All right, this is the website for the course. You can get there from my homepage if you want. And we rarely use Blackboard except to give you back grades, things like that. So all of the assignments are here. First of all, let me tell you, I do have lecture videos. That's the only part that's not up to date on the course yet. What I do is I record, obviously, I record what we're doing in class, and I post it online, including any notes I write in class. You can find them on the website. Currently, you'll find last year's stuff. Want to play around with last year's stuff? Go ahead. All right, in terms of notes and lecture videos. All right. We have 4 TAs for the class, and I see some of them sitting back here. There's Burchin. She's one of our TAs. You're the only one here right now, right? As far as I can see. So, to communicate with the TAs, please use Piazza. Information about that is down here. Okay, they will respond. Do that instead of email, even for me. We're following it. We'll answer your questions that way. We have a textbook. Here's a link to the textbook. Some of the out of the textbook. This is a pretty standard, well-used text. A lot of universities use this for signal systems. Some people really like it, some people don't. But I teach kind of in a different order than the textbook, but it is a useful resource. If you're looking for it, definitely use that. Plus, you'll need access to the assignments, so you'll have to get this book somehow. Now we have labs, and that's actually a very fun part of this class. So you'll have problem sets that are due roughly on a 2-week basis. The first one is due next Friday. And there's a box in the lab for you to hand them in. Due by midnight. You'll get a penalty of 10% a day. If they're late, we'll cut it off after 4 days. So please just get them in on time. One thing about homework assignments or any assignment you're handing in, if you have a reason why you need an extension and you ask the TAs before the shy, don't abuse it, but if there's some reason why you can't get it in this week because you're traveling or whatever, just let them know. They'll figure that out. But it has to be asked before the due date. We also have labs, and the labs no lab midterm week either, but every other week. All right. And these are handed in every 2 weeks as well. So if you go over here to these links, you've got labs. I already mentioned the problem sets. So you've got all your problem sets for the semester here, and their due dates. We also have the labs here. You see you have 5 labs, and their due dates as well. So the first one will be due approximately 3 next week, but you can start it early. So the nice thing about the labs are, even though we have space, you can in fact sign up for designated time during that specific time, and be there the whole time if you get the lab done. Right? You can work on it at home, whatever. You do need to demonstrate parts of it to your team. Now, if you just need a demo, let's say you're good at doing this on your own for whatever reason. However, if you do come to a lab session that's not your designated time, but you want help from the TA, that's perfectly fine. If for some reason the room's really crowded, please be courteous if that wasn't your sign-up time. Plenty of computers elsewhere in the room, okay, to work. Any questions about that? Was I clear about how the labs work? The labs are actually very fun. So the first one you're going to do is just very basic, getting used to MATLAB. MATLAB is a programming environment, very widely used for signal processing, for linear algebra. It's used even in industry. It runs slower than things like C and Python even, but it's very easy to get things working in. So that's why I use it. All right. And the second lab, which you're going to start doing 3 weeks from now, you're going to build Shazam. Has anyone used Shazam? Okay, I'm glad most of you know what it is. It's an app you can get, say, on your phone, where you can turn it on. It'll record whatever music is playing around you. It'll record it and identify the song, right? And we'll have learned a bit about the Fourier transform, and we're going to get you right into using it in MATLAB. To do that, music identification. You're going to build Shazam. I think it's a very fun lab. And by the end, we'll have a competition, and I give 2% extra credit, final grade % extra credit points to the winner of the Shazam competition. So I think last year we didn't. Not everyone participates, but we had like 10 people participate last year. Hopefully more this year. All right. And then some other labs. I don't have time to talk about everything. So grading policy, I have some percentage breakdown here. We have a midterm exam. This is on the website. Final exam 35%. Midterms 25%. Okay. And like I said, there's a schedule page, and this is last year's information. This has all the slides and the videos from last year, which you don't have to rush to go get it. Okay. Last thing I need to mention. See right here? There's no more lectures this week. Okay, I'm traveling, so we're not going to have lectures on Wednesday and Friday. And we'll make it up at some point. Now here. Going to shift. But Fridays will be, for now, we'll say the regular lectures. At some point, maybe we'll use them as review time, but I don't know. For now, just assume Fridays are regular lectures. Because we have this room this week, and we don't have a lecture, we're going to have the TA office hours in this room on Wednesday during lecture time. Okay, so if you come, maybe you forget it was canceled, you're going to find the TA here answering questions. The intention is to do background review on complex numbers. I'll take the next several minutes here to do what I can with complex numbers. Maybe I'll do that again next Monday. I assume that most of you have worked with complex numbers, but because it's such an important part of the class, because we use it in everything, it's worth reviewing. Before I get into this, because I'm sure this is going to go right to the last minute of class, were there any questions about how the class is run? Yeah. We usually work in pairs. Yep. You can just pair up while you're there in the lab. You each write up your own write-up. The TAs, definitely the first week, which will be next week, go to your science lab session, meet the TAs, and at the beginning of each lab session, the designated block of time, they're going to explain things. So it's good to be there on time, get started. You can leave early. All right. Okay. Let's just, what can I do in a few minutes here? Well, so in general, we're not going to restrict signal values to be real value. They can be complex values. There's a very important reason why we're doing that. Okay, you might say, well, real-world signals are real numbers. Yeah, you don't have a sensor that gives you a complex voltage. It's got a real number voltage, right? But if you extend things out to complex numbers, the math is a lot simpler when you're doing things like Fourier transform. The Fourier transform is going to explicitly use complex numbers everywhere. Of course, we know what do I mean by complex number. Well, we have a real part. So let's start with what is the imaginary number? Square root of negative 1. Call I. This is the imaginary number. Imaginary numbers simplify mathematics in many ways. One of the most immediate ways is that polynomials, if you look at the number of roots of a polynomial, it's at most the order of the polynomial. But if you use complex numbers, it's exactly the order of the polynomial. So there's one example where, going to complex numbers actually simplifies the mathematics. All right. Of course, a complex number might be something like 1 plus I. There you have a real part. There's a real part and an imaginary part. Now, the usual way to represent complex numbers is in the so-called complex plane, where you just use one dimension to be the real part and use another dimension to be the imaginary part. So this would be the number 1, negative 1 is over here, 0 is here, and up on the imaginary axis you've got I, and you've got negative I the other direction. Okay, so the number 1 plus I, let's say this number here, is just this, it would be a point in this two-dimensional space. All right? And adding complex numbers is very straightforward because the real parts add and the imaginary parts add. So let's take this 1 plus I and let's add 1 minus I. Okay, the real parts add, you get 2 plus 0 I, so it's just 2. And what we've done here is we've taken our blue number here, that was the same one. We've taken this green one, which is right here, and the sum became 2, which is this point right here. And this is just vector addition, right? If you think of these as vectors, then you've got, adding them is putting the points end to end, and you get this number out here. So it's very straightforward. Addition is straightforward as vectors. Now, multiplication is where it gets interesting. It's also very nice and easy to understand, but if you start out by saying, well, multiplication, no one has to teach me multiplication because I know how to multiply binomials. Okay, let's say, here's an example, 2 plus 3i times negative 1 plus I. All right. Now I can use FOIL, right? That's what you probably called it in, what grade were you learning binomials in? Junior high, maybe? Okay, so first inner, or first outer, inner, last, I guess what FOIL means. Okay, you multiply it out, do the 4 multiplications. Of course, in one of those products, you're going to have I times I. Right, so you're going to have a minus 2 minus 3I plus 2I, and then you're going to have minus, or a plus, this last term is 3I times I, and that becomes a minus I. I squared is negative 1. So minus 3. And there we get it back in our normal real and imaginary part notation. So you can do multiplication this way. It's less intuitive when you look at it in terms of placing these in the complex plane and figuring out where the result is going to be until you make an important, our most important identity, actually my favorite one in all math probably, Euler's identity. Euler's identity says that this e to the I t, t is just an arbitrary variable, equals cosine of t plus I sine of t. Does anyone know how you can verify this? An easy way. Yeah, Taylor series. If you do a Taylor series expansion of left and right, you'll easily see the same. All right. So here we have it in the real part and the imaginary part. So what we've done here is we've taken this so-called complex exponential function. These are going to be our friends. This is really going to be something we use every day for the rest of our lives, hopefully, but at least this course. All right. And here we've divided this up into a real part and an imaginary part. Okay. So that actually really helps when you talk about multiplying complex numbers, because it means that you can also go backwards. You can take a complex number in rectangular coordinates and put it in so-called polar coordinates here. And that's the last thing. Well, what do I want to do last? The last thing I'm going to do is just show that, let's say what polar coordinates are for complex numbers. You can write a complex number. Any complex number can be written as an a cosine, an a e to the I theta, where this here is a positive number. That's the amplitude of the complex number, and theta is the phase. And notice that by Euler's identity, this equals a cosine theta plus I a sine of theta. Any number can be written this way. We can go back and forth. And once you have things in polar coordinates, multiplication becomes easy, and we'll see that next time. But here, let's just show how do you graph it. Let's see. Where would I put that number a e to the I theta? If we're given a and theta, where does it show up in the complex plane? Again, here's 1. Here's I minus I and negative 1. And it's going to be some point where the angle to the real axis is theta, okay, in radians. And the length, the distance to the origin is a. Okay. We'll see that next time. We'll talk about magnitude, complex conjugates, real parts, imaginary parts, just to finish the background of the complex numbers. Your first assignment has a lot of this in it as well, so you can get started on your first problem set. All right, thanks. No class Wednesday or Friday, but Wednesday the TA will be here and answer